So we have been thinking about tidal disruption events for a while now, and this is part of Fitz's PhD. You'll hear a bit from Megan later on about partial tidal disruptions. But I want to basically tell you about some of our misguided thinking over the years and how you should be careful with your color bar. Takeaway message is that accretion rate is not the same as luminosity. Real simple example. This is from a previous talk where Peter Tudhill gave a little picture of himself in the infrared, which is that, if you look at me and you examine my luminosity, I'm a black body, 300 Kelvin with a pretty constant temperature, but my mass accretion rate has discrete spikes in it, probably 3 times a day, taking 8,700 kilojoules. And that comes out mostly in the infrared, right, with a luminosity of 10 to the 10 ergs per second. But the amount of energy I take in is actually a fair bit higher than that. Why's that? So? Where does most of my energy go? So there's advection and there's outflows. All right. So have this in your mind. So for example, if you look at my temperature across the day, it's basically constant. So I just look at the black body. I mean, there's some little dips and troughs, and it's a weird, looking light curve, but it's pretty normal, constant temperature thing. So in other words, your light curve doesn't really correlate with your pizza consumption. Okay, so tidal disruption events have this old theory that goes back a long way, back to 1988. And the idea is really, really neat and analytic and pretty. And it's that you take a star, you whip it through the tidal radius where the differential gravity across the star becomes more important than the star's own gravity. And that gives you a kind of nice little formula for predicting. If you say, well, this star's on an energy zero orbit, then half the star will be on bound orbits, half the star will be on unbound orbits. And therefore, you'll get a rate of return where some stuff will be on bound orbits and come back relatively faster. This stuff will never come back. So there's a distribution of mass return rates, which predicts that you can eat the star onto the black hole at a rate that goes 10 to the -5/3. So the classic observational thing to do is then look for light curves that look like 10 to the -5/3. And if you're accreting this stuff onto a supermassive black hole, you expect that to come out in X-rays. All right, so I'm kind of preempting this a bit, but then the assumption here is that luminosity should go like m dot, which should go 10 to the -5/3. But you can see already why this would not be true. And indeed, observations, which I've plotted here, show you nothing of the sort. So for a start, TDs, they are detected in X-rays, but X-rays are kind of all over the shop. Sometimes they're just not there at all. And I think we're going to unpack this a little bit later on with some of Katie's work and other people. But mostly they look like a constant temperature black body. And if you take a luminosity, you have a temperature, you can work backwards to come up with an effective radius. So just divide by sigma t to the 4 pi. And you get a radius of something so interpret these numbers 10 to the 15 centimeters, which is 100 AU. Okay, so tidal disruption events look like a 10 to the 4-ish Kelvin, 100 AU ball, which is like a star, like a giant 100 AU star that's twice the size of the solar system. And, well, according to black hole, you shouldn't expect anything optical at all. All right, so this is already weird. So most of the emission seems to be in optical UVs. These luminosities are pretty low compared to what you would infer from how much you're feeding the black hole, right? Just like saying I'm underluminous compared to the amount of food I eat. And there's a very large emission region this stuff is coming from. It seems to be just thermal radiation, and it's not anything like X-ray temperatures. It's just, an O star, basically. All right, and you get outflows, very strong outflows of 10,000 kilometers a second. All right, so this is all, and if you try to look for T to the 5/3, well, if you try hard enough, this is one of Katie's papers, the distribution of X-ray light curves, and even in the X-rays, I mean, you can basically pick whatever power law index you want between -3 and 1. So it's a bit all over the shop. I mean, there's a 5/3 in there somewhere if you want it to be there. but it's not obvious that any of that really tracks through to even the X-ray light. Okay, so there's a lot of puzzles here that are kind of not well understood, and a lot of arguments from theorists. The most it's relatively well accepted proposal, I wouldn't say it's consensus by any means, is that you must then wrap your black hole accreting X-rays into some big kind of fluffy material, just like me, that reprocesses my energy generation into infrared photons in my case. But here we reprocess it into, so you're looking at a giant ball that looks like a star. What's wrong with this picture is this is kind of a very static picture. We've already said we observe observationally that there's very strong outflows. So some models have outflows, some models don't. Some involve like a kind of really like a star, like hydrostatic. When I argue that's not the case, the other piece of the puzzle is it's actually one of the few problems in astro TDEs, like cosmology, where you have good initial conditions. You have a star and a black hole, and it's like, what happens next? It's like the universe, we know how it started, we have a good picture of it at the beginning. So it's a very clean problem. Theoretically, it's just hard. Why is it hard? It's because, real stars are kind of little small objects. So things like reducing the mass ratio, it's in GR because you're going close to black holes. So you tend to use Poisson-Chain or Newtonian approximations. Maybe just so that sort of race picture where you can predict the mass return rates. I mean, a lot of people just did that first passage of the star and then just predicted what would come back and like make a light curve from that, rather than just simulating the whole way. And then, for example, simulating stars with bound orbits. So actually, we've done a bit more of that lately. And I was involved in some of this by proxy. So, for example, here is like a really nice one, really nice piece of work from Bonnaroo. What we did was like implement a fake Newtonian potential. And the important effect of GR is that when you go around a black hole, instead of just going a nice Keplerian orbit, so these are eccentric TDEs, so the star is already bound, so there's no half-half business. But the GR effect is that if you're close to a black hole, like the precession of Perihelion and Mercury, the stream will precess and then bang into itself. And this allows you to kind of circularize material and form a disk around the black hole. And so we've recently done the same thing with a lot more effort in GR with real stars, with polytrope, and all this kind of stuff. But you see the same process taking place. Stars on a bound orbit, self-intersection of the stream leads to the formation of a disk around the black hole. Do you know what we did running this whole project? It could have saved us in 2016. We use it now 8 years. What could have saved us 8 years of work? We're using the wrong color bar. Okay, so what you miss from this picture is that we have taken 4 orders of magnitude of the highest density material in the simulation. And that is absolutely not what you look at observationally. So it's kind of neat. You can show there's a disk there and it's cool. But when we started looking at this, we actually came back after a long way around on this one. This is one from Fitz's paper. We just changed the color bar on that last image, zoomed out, and you can see there's all this fluff of bits of the stream that missed and like bits of the star that were flung out on other orbits, which is just like a huge amount of fluff that is outflowing at high speed from the black hole. And if you say, well, like, let's take a typical passage, this is like 10 to the 6 grams per centimeter squared in column depth, so kappa of 0.2. You can get optical depths of like 10 to the 5 easily. So if you like use some opacity and predict what sort of temperatures you're going to see a big fiery ball with a temperature around 10 to the 4 Kelvin. So this is good because we're making some sense of some observations. Okay, so we did this actually previous to this project. We did this with with GR, but with just polytropes, but on parabolic orbits. And it's the same deal. There's more. So again, this is just looking at the very highest density materials. The stream comes back. This is the second passage, not the first passage. So we've done the first thing and it all came back. And you do see this, little bit of circularization and formation of a disk. But again, what we're missing is just color bars only focusing on the real high density stuff here. And if you, okay, some details on we don't really have time to go into, but it's the same sort of stuff as we saw before. There is precession, it's a little bit less in the parabolic case, and you circularize material. Yeah. But again, same deal again with the parabolic case. this is what you see in, well, density and temperature if you use some kind of opacity to look at your simulation. And guess what? It's like 180 volt that is emitting in the optical and basically obscures all the inner regions. All right, so broad brush, this is pretty good. You can look at things, you know, it's like temperatures. So the thing that's actually most uncertain in this is like how deep you see when you look at it. So we want to do some proper radiative transfer. Christoph's up the back there. Been hassling him a lot about scattering. Electron scattering is tricky in radiative transfer. So making a proper observational thing about what you're going to see is tricky. But you know, you can see if you push deeper, you're going to see, you know, slightly high temperature. But you know, 2 to the 5 is the maximum here in this stuff that's outflowing. Speeds, typical speeds, you know, up to 20,000 kilometers a second, 10,000 kilometers a second. These are like around observational measurements. Well, you don't see density, so that stuff doesn't matter. But you have this reprocessing layer and the numbers kind of work. So actual light curves, so parabolic case, actually the eccentric TVs are a little bit different. So parabolic, actually, you don't send much down the black hole. That's the very, like 1% of the star ends up in the black hole, and 67% of it's still in the stream at the end of the simulation. I don't think I have that figure, but this is the one from the parabolic one. So again, so light curves are not perfect by any means, but they are in the right ballpark. So we do have temperatures which are pretty flat. We have radii of about the right size. If anything, the observational light curves seem to have a bit of a rise and fall to them, but even that, it's not. So they have seen some TDs like, you know, 5 years later, and there's still some UV optical emission going on, which indicates that maybe they are quite flat for a long time. Our light curves are like, can be bumpy as hell. In fact, from what we've done so far, very different things give you very similar light curves. So deeper penetrating encounters, different stars, different viewing angles, basically get the same thing. The only thing that really makes a big difference is if you change the opacity, so you see deeper, you start to get very different light curves out. And but simulation parameters don't seem to change much apart from that. All right, so that's the end of the story, and I'm out of time. But basically, you know, we think we have a good handle on linking these tidal disruption event simulations to real observations. And Fitz's paper is on arXiv, and out the parabolic paper will hopefully follow. But this means that we can put some meat on this bones of these, what we call Eddington envelopes, which is this optically thick fluff, is the likely solution why TVs are visible in optical and non X-rays. That's it.
Thank you.